Okay, so now we're going to be talking about why we use cosine sine functions to model simple harmonic motion. Uh, we can start this off using an energy approach. So at any given point, the kinetic plus the potential energy. Let's just use a spring system for argument's sake, or for simplicity's sake. Something of that nature. So at any given moment, the kinetic energy and the potential energy equal the total energy. Now, the energy is all potential at the moment when U, which equals 1/2 kx squared, equals 1/2 ka squared, because amplitude is the maximum displacement. So let's say the spring only comes out to here, A, that's the maximum displacement. So that's we can model the total energy and substitute that in for it. So that will yield the equation 1/2 mv squared for kinetic energy, 1/2 kx squared for potential energy of a spring, then 1/2 ka squared for the total energy. Now, if we move some stuff around a bit, we'll come up with, I'm just going to drop all the halves here. Ka squared minus kx squared. Let's go ahead and pull out the k's. So we got that. If we solve this for velocity, we will get the square root of k over m. So we have the square root of k over m, and bring this down here. So square root of quantity of a squared minus x squared. If we change velocity to the first derivative of position and keep the right side of the equation the same. Now, to solve this integral, we need to separate the variables. So I'm going to move this over here and move the dt over here. It'll look neater once I do it. K over m is constant because the spring, the torsional constant, the spring constant is not changing. The mass is not changing, so we don't need to integrate that. This, however, does need to be integrated. Now, the integral of this is just an integral rule, is the arcsine of x over a equals square root of k over m t. Now, there's a constant when you integrate. I'm just going to put it on the right side, just because it'll be over there eventually. So we're going to get rid of the signs. So if we add a sign onto both sides, I ran out of space there, but you get x over a equals kt plus c. Now if we move the a over here, we get x equals a sine of, there should be also a sine of square root of k over m t plus c. Since c is just a constant, I drew a plus sign twice. C is just a constant, that'll be our phase constant of phi. Square root of k over m is equivalent to omega, so we have omega t. My pluses and t's look the same, sorry about that. But we're also going to use a cosine since it starts at x equals 0, or time equals 0, it starts at x equals 1, or the amplitude, so it's just easier to model But if it was a sine function, it would just be offset by the phase constant, so it's not a big deal. But so our final equation is just x of t equals a cosine of omega t plus phi naught, and that's why we use cosines.